Vzhledem.
Okay, so I'm going to give a talk about asynchronous programming, but in the context of Bitcoin. So this talk is not like a beginning talk on learning how to program. I assume that you know C++ fairly advanced. It's not going to be an introduction either to parallel programming, but it's going to teach you the fundamentals or the concepts that can enable you to design applications that are highly asynchronous, but using the context of a server program which runs using threads like Bitcoin. So I'm gonna give you the fundamental concepts, and you can use those ideas to try and inform your design. And so one of the things is Bitcoin as an application, it interacts with the network and interacts with the database. You know, you're trying to do all of these operations while doing these calculations. So this is an application that is ripe to be made running in parallel. And one of the things that I've been doing is building a Bitcoin library called libBitcoin. And one of the rules that I've set myself is to have no blocking. So throughout this talk, we're going to be referring back to the fact that there's no blocking whatsoever. Another thing is when writing a library, I like to write things as a frame. I like to write things as a toolkit, not a framework. You see, a framework shoehorns you into a really particular mode of thinking. A framework is, you know, some skeleton code. You just go and add your pieces in, and you know, then it functions. It's a place for you to hang your hat. You know, hang your hat on the end of that. By contrast, a toolkit is a useful set of utilities like classes and functions that you can tie together to build an application. And you can like reuse them in any way you see fit. So with Bitcoin, there is no one right way to do it. There are many different ways. I will make strong recommendations about how things should be done, but I'm not going to tell you that is how you should do it. The background. So with libBitcoin, I was looking at Bitcoin, and we were trying to make it more scalable and robust. But then we had to like go back and rethink several things, like how do we do this? And one thing is, I have a friend who's very much into like design patterns. So I'm sure you've maybe heard of like CRTP or active object or factory design patterns, and he's very much into these design patterns, and he was always telling me about these design patterns, and I was also playing with Boostazio, and I also saw some talk by the author of Boostazio, and these things really like formed my beliefs, drive how I approach asynchronous applications. So when writing a parallel application, like a lot of people, like if you use Twisted Python uses the reactor pattern. So that's a very popular pattern, this kind of event loop. And Proactor is a one-up on the reactor pattern. So what is like a reactor pattern? So both of these patterns, the reactor pattern and the Proactor pattern, rely upon a demultiplexer. So you have all of these people, all of these users of the library, and they submit their work. They make a call, and then this event loop is like running in the center of the application. Now, with the reactor pattern, the way the demultiplexer works is that it's waiting, so it's violating the non-blocking rule which we mentioned before. It's waiting, and then a new event comes in, and it wakes up the reactor. And the reactor performs the operation. So let's say there's a write waiting to be performed. It starts to write, and upon completion, it notifies the client-supplied handler. And the whole point is that as the client, you're meant to have a function that returns very quickly, and then it goes back into this wait state over again. And whereas the proactor, by contrast, if we represent by these stars an initiate and perform of an operation, so you say that I want to start this read operation, and instead of like being notified when the operating system is ready for you to do a read, you said initiate that read and say only notify me when it's finished. So one of the things is that to support proactor, your operating system has to support asynchronous events. So the way it works is like, let's say I want to perform this operation, you submit this operation in asynchronous mode to the operating system, and upon completion, it goes to the demultiplexer, which notifies the registered clients. So from async chat in Python, the classic reactor is the way the reactor works in that particular implementation is wait for an event. So that's a reactor job. Dispatch ready to read. So that means notify me when I'm ready to read. So you dispatch this event inside the multiplexer to user handler. You read the data, so that's occurring in the user space. You process it, and then it returns back to the reactor. Where you can actually, so I mentioned before that you can only use the proactor on operating systems that support asynchronous operations, but you can actually use a reactor in an emulated mode using the proactor, you can use it in an emulator mode using an internal reactor. So the way you do that is, wait for an event, you get this read data, and then you dispatch internally to the read completed event, so you have your own internal proactor loop, and then you process the data and notify the user handler once that's completed. So one of the things is that I always thought that these patterns could only be done in the concept of a framework. So you have like your state machine with like on mouse click or on window close, on so-and-so event, this base class which you inherit from, and you override the methods and provide your own implementation. That's like the classical way of implementing these design patterns. But after playing with std bind and std function, which are now in the new C++ standard, they came from Boost originally, and with Boost Asio, it was like a bit of a revelation to me that you can instead use these function callbacks where you bind the arguments together. So the way that I use proactors is through callback functions instead of abstract base classes. So I went and like tried and made this like example Bitcoin application, and it worked, which is pretty cool. And the reason why it's so useful is because it allows you the freedom to express yourself. So here I'm initiating on a storage object, a store of like block 170. Once that block has been stored, I'm notified for a completion handler. And how that completion handler, the format has to follow is an error code indicating the status of the operation. So it could be, duplicate block already exists, or it could be, some system write failed, or it could be just nothing. And then the status of the block. So, it could say like the block is an orphan, or it was successfully added. And the different methods for the per actor can have different signatures. So this is just one example. And this error code object, it's new STD error code in new C++ standard. What it is it gives you an error code which you can test whether it's true or false. So if I do if EC, if there's an error code set, then that will pass. But if there isn't an error code set, then testing the Boolean operator on the error code object will fail. So, and you can also do equality between error code objects to see what kind of specific error it is. And so as an example, we've done our storage of the block, and then we're testing for error code cases. So if errors equals duplicate block, then, and if this block is an orphan block, then we want to request the blocks in between. If this error code had a network error or some strange reason, then disconnect the node. And actually this should say else if, and then bracket EC, that's just an error there. And then else, if there's some other error, just print the error and continue. And return. So the way that this store block works is there is this function that you call returns immediately. So you call it and it returns. And inside this storage object here is the subsystem. And you're submitting to this subsystem a piece of work that is to be completed in this thread. So you submit a piece of work to the queue dequeues it once it's ready, the work is performed, and then that callback handler at the top is called. And so you have this storage component, and many different pieces of work can be submitted to that subsystem, and many pieces of work can be going at any time, even for multiple threads, and you don't know when that can happen. It can happen from many different contexts, and so that's all like well and good, like how this like work and subsystem works, but you should keep that in the back of your head. And in general, when you're writing an application, there is a simpler model that you can use, and that is thinking in terms of asynchronous operations and the completion handlers only. So you forget about all of this, like communication with the subsystem when you do this. You can model this in a chain of operations. So here's like one such example is we have our handshake connect with the Bitcoin network, which is exchanging the versions. And on completion of that, we send to the network, to the channel that we connected to, that we want to get the blocks. And on completion of that, we send that we want to get the data for those blocks. And once that is completed, we cycle back to this to get the next set of blocks. And so you can see that like this was an initialization, and then this is a loop here. And if you're thinking in this way, you can draw these diagrams to model how your program works internally. And you can start drawing diagrams like this. It's almost like making imperative programming, except in an asynchronous way. So we've divided our program up into a set of atomic parts. that are self-contained. So, yeah, can anyone tell me what is maybe wrong with this piece of code? So we've started some component, and then something's happening in between, and then this connection object is destroyed. Right? It's when you call the destructor on this component, there could still be operations running. So this connection object is destroyed, and yet there are still operations that we'll be trying to submit to this connection object. So you have to try and maintain that the scope, the lifetime of this object remains until all of the works are finished. And the way you can do that is using enable shared from this. And when you begin your operation, you use std bind with shared from this object. And what that will mean is that this connection object will not be destroyed until all references to that object have been released. So it sticks around until the operation's finished. So you tell the operations, we're going to begin a shutdown, then the operations return, you handle them, then the object can actually destruct. Because if we go back here, once this destructor starts, this network object cannot be shut down because technically, the object lifetime in C++ is the object exists at the end of the constructor and ceases to exist at the beginning of the destructor. So yeah, there are multiple. There is not just like one subsystem in this kind of design. There are many cooperating subsystems working together. So you can have many services, all with different sets of, all running in different threads. So I mentioned before this storage object. Probably I would only put that storage object running in one thread. But maybe you have some other object which does some calculations, let's say validating Bitcoin blocks, and you would run that in a different service, but that service would be simultaneously running in several threads. And when you submit a piece of work to that service, it will choose one of these three threads to submit that work to be completed in. So the good thing about this design is that if I have some component like storage or network or whatever component, I can easily make it scale because I have this model where I'm submitting pieces of work which are being submitted to a service, and if I want to increase the number of threads for that service, all I have to do is make that service run in more threads, and it will automatically distribute the load itself over those threads depending on which threads are free or not. So object lifetimes. Okay, so there are two ways that you can model that I like to, that when I'm using this kind of paradigm, the proactors using std bind and std function for callbacks to make asynchronous applications. There are two ways, that are common ways that I am modeling, well, three ways that I'm modeling my code, that I'm structuring my code. One of them is termed pass the buck, and this is, I think this is like what the author of Boostazio calls it pass the buck, and actually it's just a set of composed operations. So in Bitcoin, before you can do anything, you connect to another node, and you have to send to that other node your version message. And that other node, if it accepts your version, should reply back with a version acknowledgement. And simultaneously, the other node should send you a version message, and you should respond back with a version acknowledgement. Only when those two sets of operations have been completed, are you ready to start communicating with that other Bitcoin node? So version exchange, finish. So the way so what I can do is, I can call this, I can make a handshake function, and I can represent it as a composed operation, which is, I start the handshake, I start the connection at the top, which is just, opening the sockets, the ports to the remote host, and then I do several things. I tell it, I send it my version number, and once, if that was successful, sending it my version number, I increment an atomic shared number between this whole operation by 1. I say that I'm interested in version packets coming from that node, and if that's successful, then I send it. Then once I actually receive a version message from that node and I verify it, I send an acknowledgement, and if that send of acknowledgement is successful, I increment the atomic number by 1. And finally, I express an interest to receiving version acknowledgement messages from that node, and if that is successful, I increment it by 1. Now, on completion of all of these events, a send version has subscribed to the Verac, to receiving the Verac. If there is some problem, because you need all 3 of these events to be completed, then the handshake connect was unsuccessful, and this whole operation fails. However, on completion of any one of these events, if this shared atomic number is equal to 3, then we know that the entire cycle has been completed, and we can actually notify, by calling the completion handler, that this operation is finished and was successful. So that is how you can represent this version exchange using this composed operation. And so for a user, it's just a very simple call where they call handshake connect, they put the IP address and the port number, and it does all of this version exchanging and such in a scalable way that if I ever want to make it scale, I can just throw more threads at it, and it will just naturally grow by happenstance. So another design used with asynchronous callback based proactors is the buck stops here. And what that is like, let's say I have some class which, so for instance, this can be one of my services or components, and there is some public member function that you want to execute on that. So I call bar. Now, if I call bar, that's going to be called from like whatever thread I call it in. But naturally, I want it to delegate to the thread that's inside of this subsystem, this component. So what I do is I post this piece of work using arguments to bar to an internal function called bar. And what happens is you see this service object up here, this service object. That's actually how I can delegate functions to what's happening inside of food, which is inside a thread. So for instance, I post do bar here, and then do bar will actually be called, will be submitted as a piece of work to the internal service. The service will pick it up and run it inside a different thread to the one that's been called from bar. It will be run inside the thread, which is the thread for food, and it will also submit the arguments, and upon completion, we'll call the completion handler to notify the caller of bar that the operation has finished and give it the information. So as I was saying before, if I want to make foo run in more threads, I can just start the service in more threads and it will distribute it over them equally. And lastly is, using the buck stops here, is it can actually, if you have 2 services or components communicating with each other, what can actually happen is that, if I I have my completion handler handle foo finished, and what happens is foo is called from the user space at the top. It calls it to the foo component, which sends it to its own internal thread here, which delegates to do foo, and then do foo makes a call to the bar component, and bar component delegates to do bar inside its own thread, and then you have finish foo, which is the completion handler to call foo. But actually we want finish foo to finish up inside this thread, because all of the stuff that happens with foo should happen in this thread, and all of bar should happen in this thread. So yeah, this is what we want. We want finish foo. So to make that happen, to make finish foo end up in the foo thread, what we'd have to do is something similar to this, with a finish foo and a do finish foo. So what you can actually do is use a strand. And a strand is a type of object which you can think of as a set of exclusive callbacks. So with a strand object, you populate it with a set of callbacks, and you can only call one callback at a time. And when you call that one callback, it is exclusive to all of the other callbacks inside of that strand object. So one way of using the strand is in this case. So like, let's say, just as an example, if I create 3 strand objects and I call them all together like this, as long as this is outside of the strand, then even though I've called F2 with F3 and then F1, actually what will happen is that it will execute in order of it will first execute the function print1, then the function print2, and the function print3. So it guarantees order because it uses the dispatch method. So here's an example of one. This is called from one component, and this one component is called the kernel here, and this kernel wants to ask the storage component to do some piece of work, and then once that piece of work is finished, it wants to resume what it was doing, and instead of having to have this finish fetch block locator delegate to do finish block locator so that it crosses back into the thread boundaries, what we can actually do is use a strand wrap to automatically submit that work back into this component. So let's break down this function. There's a storage component which wants to request the next block locator. So we submit to the fetch block locator our completion handler, and the completion handler is this callback which we've wrapped in strand bind to make sure that each of the calls are exclusive, and the actual function will call request next blocks. So it will call the member function of kernel with request next blocks. Argument 1 will just be argument 1, and argument 2 will be argument 2, and then we bound this piece of info that we want to keep around for the lifetime of that work until that work is completed. So using this paradigm, we can now have finish foo delegate directly back into foo because we used a strand object. So yeah, actually in these systems, so actually one of the things is, so now we've been talking about like fixed sets of operations so far. So A calls B, calls C, calls D in this nice chain of objects. But actually, like what can happen in especially like networked applications is like everything is calling everything, and you don't know what's going on. Like and anything can call you at any time whenever you want without like totally unexpected. So like things are unexpected, things are like random, things are unordered. There is no discernible sequence. So how can we model this using parameters and callbacks? Well, what we could do is, the way I do it is you express interest in having some kind of, you express interest in this event, and then once this event has occurred, you are notified. So with the network component, what you do is you say, I want to subscribe to inventory packets, and I want to subscribe to inventory packets for this host, and when you get those, please call this function called receive inventory. And I want you to pass the host ID as the first argument of this function, but then this argument is the argument that you call the function. So this will be the actual this will be the actual function definition for that receive inventory. So if you see receive inventory here, you know, kernel receive inventory, and then channel handle and an argument that is passed by the network component. So yeah, that argument passed by the network component will be the inventory packet itself, and this is the channel handle. So after a subscriber who has been notified of an event, they are automatically removed from the queue, and in order to maintain being subscribed to a certain event, you have to when that function is called, it has to resubscribe to that event, so you get this loop. The reason it's done that way is because you don't have to have these semantics where you subscribe, unsubscribe, and this is like a far simpler way because you can control the resubscribe semantics. You don't need to like, let's say, make a timer that will like resubscribe you in a second. If you have like some conflict where you subscribe to an event and then you're called but you're still subscribed, and maybe you like want to miss one event because you want it to be called from another function. So this actually offers much nicer semantics. Alright, so that's basically the talk. My name is Genjix. We have a free node IRC channel, Bitcoin consultancy. My name is Amir Taaki. Alright. And were there any questions?
Yeah. How fast is it?
Well, because we're not ever blocking, it's very fast, because you don't have to, like a future and a promise, like where I say like, if I create a future object and then I ask for the promise to like give me the object back, in between there you're blocking the thread, so nothing else can be submitted to the thread. But like this, with this design, nothing ever blocks. There is no blocking whatsoever.
It just means there are some functions like sorting when you want to guarantee order and things like that, and I think they are not really, or I can't imagine how they can be really fast, like doing this all the time and things. But maybe if it's implemented.
Well, because there's things like a lot of the problems with like making like asynchronous applications is the problem with bugs, because they're really hard to conceptualize. So one of the things with this is like giving you a set of tools that you can use to like model parallelism in a very intuitive way. Yet at the same time, something like the reactor pattern has like this problem with the blocking, and that you need like to inherit from some abstract base class, which is very restrictive, especially like when you start to build applications that are very big. Like when you're in a very like simple level, maybe like one thread or two threads, and you only do like one or two things, then sure, like a finite state machine is okay. But like once you start getting to like millions of operations and lots of threads, then you need to have some scalable design. So I think that was all the questions.
The subscribing and resubscribing, doesn't it introduce race condition? You know, with the Unix signal, there was the same pattern. Signal registered a handler for a signal coming to the process, and when the signal handler was called, the signal handler was uninstalled before the call, so the signal handler had to reinstate itself. But when another signal came, in between the reinstation, the default handler would be called and the process would be terminated.
Yeah, you have a point, and it's what is happening is, like, when you subscribe, if you subscribe to some component and you register your callback, and then that component like switches into another thread to register that component, what can happen is, while it's being switched to another thread, the event can come through. So the way around that problem, to do that, is that when you subscribe to an event, it's done within the same thread. So a subscribe is done immediately, as soon as you call. So that ensures that you won't miss any events. And
what if there are more than one threads handling the event?
well, because you know, like, each call is in order to have in order for the operations to be what's the word, thread safe, to not to have these race conditions, they are actually put into a strand object, and the strand object executes each one of these events exclusively. So there is no potential for race conditions there, because you're executing one of these events in the strand object, and if that event wants to be resubscribed to the event, it notifies the component straight away and is resubscribed straight away within the same object. And then you notify the next one. And if new events are coming in, well, then it either happens before or after this event, but not during the same event, because there is this exclusion between being notified and other events notifying other events.
So are events queued?
Pardon?
Are events queued? Incoming events while one event is handled and another event comes in?
Events aren't queued, but rather work is queued. So if I create a function and I bind some arguments to that function, I submit it to the service, and that service, once it's ready, will wake up and call that function. So what you do is, instead of creating an event, you create the function which is already ready, and you submit it to the service, which then runs that in exclusion to the other pieces of work, and then that piece of work will notify all of the completion handlers.